Section 1.2, we're going to talk about function behavior and end behavior limits. So some of this is going to be language you've seen and heard before, maybe defined a little bit differently, though not drastically. The first set of information you have heard before, I'm quite sure. The words increasing, decreasing, and constant. So an increasing function is as input values increase, output values increase. All right, so if you go from x equal 1 to x equal 2 to x equal 3, the y values also go up. If a graph is decreasing, then as the input values increase, they go from 1 to 2 to 3, the output values go down. They decrease. And if a graph or a portion of a graph is constant, then as the input values increase, the output values remain the same. So of course, visually, increasing means you're going uphill. Decreasing means you're going downhill. And constant means that it is flat. Now, a whole graph doesn't have to be doing one thing or another. It can change throughout the graph, but whatever portion looks like this or has these characteristics will be increasing, decreasing, or constant. So this is one way to describe a graph. You're describing how the values are changing, right? There's another way to describe a graph, and that actually talks about how the curve looks. Not just how it's changing, but how it looks when you're looking at the graph itself. That's called curvature. You usually see this mentioned the first time in maybe like an Algebra 2 class in high school when you're talking about parabolas. Okay? When you're talking about parabolas, you usually have a teacher describe these two graphs right here. And the first graph that's drawn is called concave up. The second graph that I drew is called concave down. Does that look familiar? Have some of you seen that before? Good. So a concave graph is a graph that opens upward. One way we can sometimes describe it is that it holds water. A concave down graph is a graph that opens downward or dumps water. Now, before I move on to the other two, it doesn't have to be just one or the other. It could, again, have portions where it's concave up and portions where it's concave down. And it also can look like it's sort of halfway. This would be a graph that's still opening upward. I know it doesn't really hold water, but it is still opening upward. So this is still concave up. And this graph, it would still be concave down. It still has that same curving feature to it. Now, a graph that's neither is not one that changes. Okay, so like this graph has portions of it that are concave up, namely this part, and portions of it that are concave down, namely this part. Okay? And neither graph is actually a graph that doesn't do either of those things on that portion of the graph, and that graph would be flat, and it would be a line that's flat like this, constant. That has no curvature. And then an inflection point is a point where the graph changes concavity. So obviously not every graph has that. These graphs right here don't have that. The whole graph is one thing or the other, concave up or concave down. But this other graph that I drew over here, right here in the middle, it changed between the pink and the yellow. And that point where it changes concavity is called a point of inflection. Okay, does everybody have all those written down? All right. So we're going to take a graph and we're going to do some identification of these features. So it says to identify the direction and concavity of the function. So direction has to do with whether the graph is increasing or decreasing, or neither. And concavity has to do whether it's concave up or concave down, or neither. So we're going to identify 4 potential pieces of information. Where is it increasing? Where is it decreasing? Where is it concave up? Where is it concave down? Okay? So we always identify it based on the x values where it's happening. Always based on x. So let's do the increasing part of it first. Where does this graph appear to be increasing? All right, so it looks like right in this portion of it, it's increasing. Do you agree? Anywhere else? Yeah, so we have to be careful because that negative 10 is actually a y value. Any idea what the x value? Well, it's not marked, right? But it's something over there. What do you think? Negative something. It's infinity. So because they're not indicating anything better, it would be better if this graph were like this. I'd be much happier. But that's what they're inferring. They're inferring that it continues in that direction. So if we continue in this direction downward forever, then the x values are also decreasing forever, right? It's going left forever. So let's write down what's increasing. This graph is increasing from negative infinity to 0. And I do want to pause here for a moment because there is sort of what appears to be sort of a flattening out right here. So it does stop increasing, albeit briefly, right? And then it picks back up again. So then it's also increasing from 0 to b. Now, this is interval notation. I hope you've seen it before. Interval notation is going to either use parentheses or brackets. A parenthesis is used when you cannot equal a value, and negative infinity is not a value, so we can't equal it. It's a concept, right? This idea of getting negative forever. 0 is where it has this brief moment where it stops increasing and then it starts back, so we don't actually increase at x equals 0 either. And then again at b, what's going to happen if we continue on just slightly past b? It's going to start decreasing, so we've got an open interval endpoint on that as well. So these are all parentheses. The u in between is not super crucial, but it's set notation. This says union. It means this piece and also the next piece. So that's a union notation. Let's do decreasing. Where does this graph appear to be decreasing? Right over here, yeah? Okay, so it starts at b. Again, we read graphs like we read English from left to right. So it starts at b and then it continues along until we get infinitely large. So we have infinity over there. So this would be b to infinity that it's decreasing. So that's the direction. So whenever it says direction, it's talking about the increasing versus decreasing features of our function. Concavity, or curvature, is going to talk about concave up, concave down. And typically we read again the graph from left to right talking about curvature. So if I start over here at negative infinity and I'm moving along the curve, that's the blue part, what's going on right here in this portion of the graph? Can you tell? The concavity. It's concave down. This piece is concave down. And where does it sort of stop being concave down? It looks like it still hit 0, right? Because what happens after 0? It's curving upward, right? So our curve is concave down from negative infinity to 0. Now, it doesn't have to always be increasing and concave up or concave down at the same time. None of those features are mutually exclusive. So this one is negative infinity to 0 on the concave down. And then we said from 0 to something, it's going to be concave up. What do you think? Where is it going to stop being concave up? Yeah, it looks like, and that's probably why they marked it on the graph, right? If you take a look at that particular point A, so I just traced up from the point A, that's where I am. This point looks like it's changing, right? This piece is concave up. What's going on over here? Concave down. So what would we call point A? An inflection point, or a point of inflection, exactly. So let's identify then it is concave up from what to what? 0 to A. And then it continues on after the original piece that we talked about being concave down, and it's concave down from A to what? A to infinity. Very good. So do we need to list B in there? Not at all, because nothing happens at B that changes it. So from A to infinity, it continues to then be concave down. Okay, anyone have any questions on that one? All right. Problem. Oh, yes, I'm sorry, yes.
Why didn't we address, like, do you have to say that it's constant at 0, or do you just leave it as?
Yeah, so when we're looking at concavity or at increasing, decreasing, we always talk about it over an interval. So yes, something happened at 0 and at A as well that changed pieces, but it's a specific location, a point in time, not an interval. So we don't have to address that. It's a good question. And let's see, I think we got all the directions in there, didn't we? Yeah, we did. Okay. Problems like this are the primary reason that I have notes printed for you, because I don't want you to spend all the time it takes to write this problem down. And the more we go into this class, the more problems like this and tables we're going to have. So this one talks about the percentage of people in the United States who earn at least $T,000. So T is between 25 and 150. So what would T equal to 25 mean? $25,000. Okay, so this would be somebody making $25,000. What would 150 mean? $150,000, okay? So T is representing in thousands what's going on. It says it can be modeled by P of T equals, they give you an equation, percent. So this equation is going to tell us what the percentage are of the people that make that much money, okay? So it says, is P increasing or decreasing on the interval? And then what is the concavity on the interval? So we need to look at a graph, right? So we're going to grab our calculator and we're going to look at a graph of this particular function. All right, so we're going to put in $119.931 parentheses. Oh, I guess I put in 119.931, and then 0.982. The caret key over here is the one where you get the exponent right there. So a caret. And then I need the variable, and the variable that our calculator will use is this one right here, x. So I have the equation into the calculator. I don't really know exactly what I need my window to be, but they do give me some information. What's the information they give me that I'm going to be concerned about? I don't have this set up here now, but what did it say that's important about their variable that's the input? Exactly. The input variable that we care about, or at least the portion of this graph we care about, is between 25 and 150. So when I'm looking at my window, that's the portion of the window I need to be looking at. So I'm going to hit window, and I'm going to make my window go from 25 to 150. Now, there's a cool feature on your calculator that will allow you to not know what the output is, but still give you a good window no matter what the output is. Okay, some of the times it's like, okay, I know one of the variables. I know the input's supposed to be between this and this, but I don't know what the output's supposed to be. So do I just play with the window until it works? You could, and you might get lucky and it might work quickly, or it might not, right? So what can you do? All right, well, there is a button called Zoom Fit. So if you hit Zoom and you arrow down, it's option number 0, Zoom Fit. And what Zoom Fit does is it fits the best Y minimum and Y max to the X min and X max that you put in, which is awfully handy. So we're going to select 0, so you can either type 0 or hit enter along on the 0. And it is going to graph from 25 to 150. This is 25. This is 150. Now, it doesn't necessarily mark out for us what the max and the min are. We could look if we wanted to. Now, if you hit window, it'll tell you. It's letting your minimum be 7.86 and your maximum on Y be 76.15. So you can see that. But this particular picture is all we really cared about for the questions that were asked. So everybody good so far? Okay, so I'm going to copy this, roughly, this image over here onto here. So the interval looks something like this when we went from 25 to 150. That's a terribly rough estimate, but it's enough for what we need. A question asks, is P increasing or decreasing on the interval?
Decreasing.
It's decreasing. Now, I want to pause for a moment and just consider the context of the problem. Does that make sense? Conceptually?
Yes.
Yeah, conceptually that should make sense because there are fewer people making $150,000 a year than $25,000 a year, right? So you would expect that the percentage should go down as the dollar amount of people's salaries go up. So that seems reasonable. The second question is about concavity. What's the concavity on the interval? It is concave up. Make sense? All right. Our next portion of the title of this lesson was about end behavior, what happens on the end of a graph. So what is end behavior? An end behavior refers to the behavior of the output values as the input values either become large or small without bound. So the large or small without bound means that we are approaching infinity or negative infinity. That's what it's referring to. So as the graph goes to the right forever or to the left forever, what's happening? The next pieces actually have some notation. So I'm going to let you jot those down because it's a lot of writing, and then we'll talk about what it's actually saying. I know a couple of you are still writing. I'm not going to change my screen, but let me talk through what some of this is saying. There's some notation. Those of you who've taken calculus before have seen it before. Those of you who haven't might not. The notation is right here that I'm talking about, and it's up there too, this piece. This notation is notation for limits. We're going to talk more about them in the next section as well, but this is telling you down here below it that the x value is approaching positive or negative infinity. So that means you're going either to the left or to the right of the graph forever. That's what that means, okay? The word limit above it means that it's asking you what the y values are doing. What is happening to the y value when you go to the left and to the right of the graph forever? Does the y value increase forever? Does the y value decrease forever? Or does it somehow level off somewhere? And those are really your three choices. I will take that back. It could do something like a trig function where it oscillates, right? That's a possibility as well. We won't be doing trig in this class, but that is a possibility. All right, so the first one up here tells you that it actually levels off somewhere. It equals L. There's some point where you have a graph that's leveling off. So let me draw a picture of what that would look like if it did that. So a graph that actually has that kind of a feature would be a graph, and you've seen this graph before, where it looks like this. This would be the graph of what's called an exponential, like y equals e to the x, but negative. It would be flipped around. And if you go to the right forever on this graph is leveling off at the x-axis, which is the value of y is 0. Okay? So one possibility is as you go to the left forever, the graph levels, or left or right forever, the graph is leveling off. Now notice the other half of the graph doesn't do that, right? What happens to this half of the graph? It goes up forever. So that's increasing without bound. It's going to infinity. So in some sense, this particular picture right here, this piece fits this description, and this piece fits this description on different sides of the graph. Now, a graph could have in such a case where it actually fits one of the descriptions completely. So imagine you have this graph. On both sides, it's decreasing forever, right? Negative infinity, straight down. So it doesn't have to sort of fit into both descriptions. Sometimes it will, sometimes it'll fit into one or the other, and sometimes it'll fit into both. So we're looking at the end behaviors, the parts where the arrows go on our graph, and talking about what happens there. So we're going to do an example of one, and this one you're going to need your calculator for. So grab your calculator and put in f of x equals 1.5 to the x. And there's nothing in here, like on the last one it was really nice because they gave us that interval, right, 25 to 150. There's nothing in here that tells us what we want our interval to be. So we're just going to put it in that standard window because we don't have any other indication. So the way we do that, remember, is we hit zoom and it's number 6, standard. And that's a graph that looks an awful lot like the one I actually just described. Actually, I mean, it's flipped around, but it's very similar, right? Half of it's leveling off and the other half of it's not. So it says to describe the end behavior verbally. So that's the language we talked about in the last section 1.1. Verbally means with words. We're not writing any math symbols down. We're using our words only to describe it. Okay? Now, if you don't use complete sentences, I'm not going to freak out on you or anything. But it should be readable so that I know what I'm talking about, or that I know that you know what you're talking about. Okay? So I need to be able to make sense of the English that you do use on there. So, as we're taking a look at this, how would you describe, actually let me sketch this graph before I turn it off. How would you describe this graph's end behavior verbally? What is it doing? We have two ends, the left hand and the right hand side, right? So, when we're describing the end behavior, we're going to talk about the input. So as the input, if you want to say, you know, the x values, that's okay, but as the input increases, aka as the graph goes to the right, that's input increasing. What does the graph do? It goes to infinity, right? It increases, we say that increases without bound. Okay, so as the input increases, the output increases without bound. Okay, so that's the right-hand side. Now we need to talk about the left-hand side. As the input what? Decreases. So it goes left forever. So as the input decreases, what does the output do? Good. That's fantastic language. Yes, the output, oh, I got ahead of myself. The output approaches 0. Some similar language you could use is you could say that it levels off at 0. Or it tends towards 0. This would all be language that mean the same thing. But the idea is that if the input's going left, it's decreasing, then the output's leveling off at 0. It says to write limit notation for the end behavior. Okay, so limit notation is going to have that LIM. Underneath it, you're going to have the input variable. And in this case, the input variable was indeed x. Whoops, I didn't mean to flip screens. Right? The input up here is x. So we're going to write x. We have two pieces we're going to write down. We have to do the limit as x approaches infinity. We also have to do the limit as x approaches negative infinity. So the infinity one is the increases without bound. It's the first description that I wrote. But it's the limit of something. You can't just write limit x approaches infinity equals. That would be writing like square root equals 7. Well, square root of what? Are you guys with me? You can't just write down square root equals. You can't just write down limit equals. Limit means nothing except for what you write next to it. It's the limit of our function. The limit of f of x, because that's the name of our function, equals. So here's where the equals occurs. Limit as x approaches infinity of the function f of x equals. Okay, so on that graph, this is the first description we put. What does the what does the output do as the input increases? It increases without bound. So what value is it approaching? Infinity. So we say that this limit is equal to infinity. Not because infinity is a number, but because that's how we represent that something is increasing without bound. It's tending towards something infinite. Now, the second one also needs that f of x next to it, so make sure yours has one. This one says the limit as x approaches negative infinity. So this is the decreasing x values, the left-hand side of the graph. What does this one equal?
0.
This one's 0. Now, it doesn't matter that we don't actually get to 0, but it's what we're getting close to that matters. We're approaching 0. Okay? There's a sign at my daughter's school, and it says, I'm probably not going to say it quite right, and it's a famous quote, and it's on the wall. Somebody in here is from North Rock Creek. Do you remember what it says? It's above the cafeteria window. It says something like, if you shoot, it says something,
If you shoot for the stars, or you shoot for the moon, it doesn't matter if you land among the stars or something.
similar to that. It said, perfection is unattainable, but if you shoot for perfection, you'll hit excellence. That's the idea. You're getting closer to it, right? You're getting closer to it. It's more approaching what you want. All right, so this one says to write an equation for any horizontal asymptotes. Now, a horizontal asymptote is, in fact, or an asymptote in general, a line that you get close to. That's what it is. Is there a line here that we are going to get close to? Yeah, what is it?
0.
It's the x-axis, and the equation for the x-axis is what? Y equals 0. So make sure when you're asked for an asymptote that you write the equation. So don't just write down 0. 0 is not an equation. Y equals 0 would be an equation. X equals 0 would be an equation. Because this is a horizontal line, it'll be y equals 0. All right. We're going to talk about some numerical estimation, which will lead into the next section as well. When estimating numerically, we are going to increment by adding or multiplying by a constant value, or constant, until a pattern becomes apparent. Okay, so in order to estimate something numerically, we have to get closer, and we're going to do it in a structured way. We're not going to just say, I'm going to get close to the value 0, so I'm going to choose 10, and then I'm going to choose 5, and then maybe I'll choose 1, and then I'll choose 0.6, and we're going to do it in a structured way. We're going to do it incrementally by adding or multiplying by a constant until a pattern becomes apparent. We're going to need at least 4 estimates. And in our table, we're going to show at least 4 decimal points. And you need 3 entries that are identical before you stop. That's what that's saying. At least 4 decimal points which remain constant for 3 entries when a limit exists. So these are some guidelines on how to do this. And then we're going to do one. Is everybody good? All right, this is our equation, or our question. Limit as t approaches infinity of 6 times the natural log of 10 plus t to the negative 1. And it says to numerically estimate. Okay, so here's a pop quiz for you. Not a for real pop quiz, but just let's see what you remember. What does the word numerically mean from last time? With a table. Anytime you see numerically, it means with a table. So if you see the word numerically, and I'm grading your paper and you have done anything but a table, you didn't do the problem right. At least not the method you were asked to do it with, okay? With a table. So we've got an equation. The equation part of it is right here. And that part is what we're going to put into y1. Okay? It says that we are going to start with t equal 500, and we're going to increment by 5,000 to estimate. So it's telling us how we're going to do the incremental estimations as well. So let's go ahead and enter this equation into y1 and go from there. So we have 6 natural log of 10 plus, and then of course we're going to use x because that's what our calculator is using in the place of the t. Do the caret and -1, and to make sure you're using the negative button that's down here, okay, for -1. This is why we wanted to go ahead and get our calculator set up to do tables from the beginning today, right? Because we're going to use them now. So hopefully you went through those steps. If you didn't, or I lost you along the way or whatever, make sure and catch me after class so we can get your calculator set up to do this right, okay? Because what we want to do now is we want to go into the table. We get into the table by hitting the second button and graph. We can delete out what's here. If you can't delete, then that's the part where I need to help you fix your calculator later. You should be able to delete if you've set it up properly. And it said we're going to start at 500. That's what the directions said. Start t equal 500. So that's good. 500. There we go. 500 is our first value. After we write that one down, it says that we're going to increment by 5,000. So if the first entry is 500 and we increment by 5,000, what will the second entry be? 5,500. And then we're going to increment by another 5,000, which is going to give me 10,500. Now, it said I need at least 4 entries, right? Or 3 entries that remain constant. So take a look on here. They have to remain constant to 4 decimal places, and these aren't even constant at the 3 decimal place mark, right? They differ. This one has a 7, and then the bottom 2 have 6s. So I need at least one more value, for sure. What would the next value be after 10,500? 15,500. Now I stand a chance at this being enough, but it was supposed to be the same to 4 decimal places, not 3. And all I see are 3 on here, so what am I going to do? I need to look at each of them individually, and you can do that by arrowing over to them. Now we're going to write these values down, and we're going to write them down to 4 decimal places. So our first y value we're going to write down is going to say 13.8167. So as we do this, let me flip back over here so you can see what I'm writing down. I need 2 screens. That's what I need. Oh, goodness. So you need a table. Your table needs to have t in it because our variable was t. If your variable were k or x or whatever, you'd put that over there. And then the other one, we'll call our function f of t. It doesn't give us a name because it already put it into the limit itself, so we'll just call it f of t. We said that this is 500, 5,500, 10,500, and 15,500. So we had all of that on our screen before. And I'm not going to flip back over to it because you've got your calculator hopefully as well, and I'll just write down what mine is saying. The first one says 13.8167. An arrow down. The next one says 13.8156. The next one says 13.815, and if it's rounded, it'll be a 6, right? I'm not sure if you guys are seeing it from your screen or not. I'll put it back on here in a minute. The next one is 13.8155. What did it say I needed? It said I need 4 decimal points listed, which remain constant for 3 entries. And do all 4 of these decimal points remain constant for my 3 entries? No, the last one was different, wasn't it? So I need to go further down in my table. 15,500 is the last one I did. What would be the next entry in my table? 20,500. Okay?
So,
Yes?
what is the question asking when it says estimate to 3 decimal places?
We're going to give our answer to 3 decimal places, but we want the table to match up to 4 decimal places before we give our answer because there might be rounding involved if we're not careful. That's why. So I'm going to put in 20,500 here, an arrow over on top of that. My calculator says that is 13.8155. So that's 2 entries that are matching to 4 decimal places. What would be after 20,500? 25,500. And we hope.
Keep going until you get 4 in a row.
Yes, we're going to keep going until we have 4 decimal places in a row that are exactly the same. And that one, actually, I think that one works. Yeah, 13.8155. So these are the 3 matching ones that I was looking for. Exactly the same to 4 decimal places. And then my answer is supposed to be correct to 3 decimal places. So I'm going to use these values now, and I'm going to write down the answer using rounding to 3 decimal places from those values. So what would my answer be with rounding for 3 decimal places?
13.816.
Yes, 13.816. This would be my limit, numerically.
Do you have to put the limit as purchase?
Yeah, I'm going to do that next. So our answer would be that the limit as x approaches infinity of f of x, because that's, and I'm sorry, we didn't have x, we have t, don't we? Let's use the right letter. As t approaches infinity of f of t is equal to 13.816. If you switch it from x's and t's, I'm not going to freak out on you, but we'll try to be consistent so that the variables match. Any questions on that one? All right.